Okay, so let me share the screen with you. Okay, here we are. So here is the quiz one questions, and we're just going to look at answers today. Just to again make sure, because the ones that I sampled gave me, we thought that we need to discuss this in more details, right? So let's take a look at that. So how would you do, let's do the part B first. That's the easiest one. And delta I j epsilon I j k. How would you go about even handling this, right? So that's there are two ways of doing this. Let's do the brute force simplest way first, right? So any index that's being repeated is going to get summed over and so on, right? But then there is a simpler way also to do that, but that just gets very quickly very lengthy, because I, j, and k, all of them are an element of the set 1, 2, and 3. And so you can see quickly you end up with lots of different possibilities, and it gets very lengthy. So any thoughts? Anybody has how you would want to do it? Okay, let's eliminate the Einstein summation convention. Write down the summation signs explicitly. How would then look? How many summation terms do I need? Anybody? Which indices are being summed over? You can just tell me that.
I and J.
I and j. Okay, so I and j. So I'm just going to need two summations, delta ij, epsilon I j k, right? And so let's think about this. Let's just write down, there would be 9 terms, but I can write some of them, right? So I'm going to start with I being 1, 2, 3. So I'm going to write delta 1 j epsilon 1 j k. Okay. And sum over j is still there. Then the other term I'm going to have, let me make a little room here. Plus I'm going to have delta 2j epsilon 2 jk plus delta 3j epsilon 3 jk, and that takes care of it. So getting rid of one summation allowed us to do this. If you add the second summation, you are going to, but you can be clever about it, right? Over here, which one of the, since you know the properties of the canonical delta, which one of the j's will survive? This is going to fix the value of j2. If you sum over j, you are going to have delta 1, 1, delta 1, 2, delta 1, 3, right? So these things expand out, sorry. These things expand out to delta 1, 1, delta 1, 2, delta 1, 3. Which one of these are 0?
Delta 1, 2, 1, 3.
Right, okay. Right, so these two are equal to 0, right? I'm just going to add the plus sign. This is non-zero, but how about that one?
It's gonna be 0.
It's going to be 0. So the index repeats. If the index repeats in epsilon ijk, then this term is going to be 0. So the last two terms are 0 because of the Kronecker delta. The first term is 0 because of the Levi-Civita. And so all of these terms are going to eventually add up to 0, and you get 0. Right? Everybody with me? Does that make sense?
Yes.
Okay. So that's easy to see when you expand it out, but there is still a lot of work. You have to keep track of it. So you want to avoid bookkeeping as much as you can, because bookkeeping is at this level, it can be messy and you can actually add mistakes. So let's look at it slightly differently. Epsilon ij, epsilon ijk, right? What does this tell you? Without bringing in the summation signs now, you know what we do when delta ij kind of terms come. That means I needs to be equal to j, right? So that means you need to, in this expression, I, or rather, let's take the second index, is to be replaced by the first index, right? And so you get basically then delta I, epsilon. Now these are specific values of, right? So delta I would be 1. That's not getting summed over, even though it looks like that. It's just specific value of I, right? And then epsilon I, k, and you know this is 0. And so the answer is going to be 0. So you can figure that out in just 1 or 2 steps by using the definitions, and you don't have to worry about any kind of bookkeeping. It is identically 0. Does that make sense? Is everybody with me? You see the thinking process. So these things here, which I'm going to highlight, are crucial. Delta function means this, right? It's an important kind of rule of thumb. And then in the remaining expressions, if you get rid of the deltas, then the remaining expression requires a specific substitution that's dictated by the delta function. Everybody with me? Okay. Make sure you sort of understand how the thinking goes. Now let's take a look at, let's see if you have any questions about this. Any questions? And this thinking is important, not just in physics. You know, when some of you will take advanced physics classes where you need the tensors. For example, if you want to do the combination of electromagnetism and relativity, you need those tensors. You need to do quantum field theory, you need those tensors. Some of you may not even do that, but maybe you are doing some, computational problem, or want to learn about this new techniques of machine learning. It's all based on tensors because you have multidimensional functions, functions of multivariables, and whenever you have that, you get the language of linear algebra. You need vectors. To transform vectors, you need tensors, and so on. And so understanding tensor notations is actually very, very useful, even in some of the advanced applied areas. Yeah, and even if they're not directly related to physics, though machine learning actually is being applied to lots of physics problems very recently. And let's see what was, if I want to give you one of the coolest example, it would be, so in the lab last semester, if you took the quantum measurement lab, you had to put in specific optical elements based on the outcome that you wanted to get. They have built now, based on machine learning, they have built a device that can take randomly different optical elements. So of course, this was done as simulation first, and then they saw this experimentally. In the field of optics, non-linearities are very crucial, very important, because they allow you to do things that you could not do with linear optics. And so if you want a specific non-linearity to be experienced by the light fields in your experiment, and you are expecting a certain output, you can actually give that to a machine learning algorithm, and it's going to tell you, these and these are optical elements that you will need in this specific order and such. And that is the information that you don't get by, maybe several years of experimentation. So several of years of experiments, trial and error have been eliminated basically completely by using these machine learning techniques. And so if you get a chance, learn about it. These things are pretty cool and pretty useful for a variety of different things. So let's take a look at the epsilon ijk now. Epsilon ijk, epsilon ijk. And I gave you the delta function expansions of the product of the two Levi-Civitas. So let's use that. The Levi-Civitas directly are are very difficult to manipulate. And so you always want to see if you can convert them into the delta function. Then that makes life a little easier. So anybody who wants to help me here, how would we do this, right? So it's kind of easy.
Delta JJ.
Delta JJ,
Delta
delta
KK
K, okay,
minus delta JK.
JK, delta
Delta KJ.
KJ. Okay, very good. Now you can see easily here that if these terms, these are delta JJ and delta KK, right? So these things are just being summed over. And so, and the indices are the same. What's the value of delta JJ when the index is being summed over?
3.
Anybody knows? 3. Okay, very good. So sum over J, delta JJ is 3 because it's delta 1, 1, but delta 1, 2, 2, and delta 3, 3. Sum
And
over
same for
K,
KK. Yeah,
delta
it's gonna be
KK
3.
is also going to be 3. But when, what would happen to this thing? Any thoughts? Now delta
It
JK and
equals,
delta KJ is exactly the same, right? So you can even write it like this. And you have sum over J and K. Okay.
I think that one goes delta 1 1 multiply delta 1 1 the type,
Mhm.
and then
Okay.
plus delta 2 2 plus multiply delta 2.
Right. When J and K are the same, then you're going to have, so let's expand this out, right? So let's see what we get. So delta 1, and when you have, well, let's leave summation K as it is. So you're going to have delta 1K squared plus delta 2K squared plus delta 3K squared, right? And then only one of the terms will survive. So only K equal to 1 will survive here. K equal to 2 will survive there. And K equal to 3 will survive there. So only one of the terms of the summation over K contribute, and you basically get 3, right? Everybody okay with that?
Yeah.
And the first term is the product of these two. And the second term is that. So you get basically 9 minus epsilon I j k epsilon I 9 minus 3 equal to 6. Is that correct? You think?
Yes.
Okay, very good. Okay, so that's that looks fine. Yeah, it's because of the double summation that the other terms survive. Okay, very good. So you got that. Any thoughts, questions, concerns? Okay, then let's get started with our usual business. Let me just recollect what we were doing last time. So before the quiz, we looked at the Stokes theorem, and then one special case we proved it, right? So we looked at basically the divergence theorem and the Stokes theorem, and those are very important. These are essentially workhorses of electricity and magnetism to manipulate expressions and make them simple, right? So it allows you essentially to solve problems that otherwise would be difficult to solve because of the idea it's there. So let me do one more thing here. Okay, let me stop sharing because I lost the track of where it was. Or it just goes away. Okay, very good. So it's here. Now let's take a look at a couple of things which are related with what we were doing. So after you have understood the Stokes theorem and the divergence theorem, then we can use those to generate so-called Green's identities. And these Green's identities are again another calculational tool that helps us simplify some of the work that we need to do to determine electric and magnetic fields given the charge distributions and the current distributions, right? So we are going to use the divergence theorem. Right, let's take the expression from here because we have it all written down. Okay, so that's our divergence theorem. Divergence, integral of divergence over a volume, so a certain specific volume is equal to the flux coming out of, right? So this is the flux of F coming out of the surface, right? That binds that volume. That's the boundary of the volume. So it's a finite volume. That's crucial here. What we're going to do is change this F, which is taken to be a function of R. That's what the quantities in the in ENM are, their functions of position, is a combination of phi and psi, two scalar functions, two scalar fields, where of course, F is a vector field, so you have to bring in the vector character somehow, and that enters here through the gradient operator, right? And so you do divergence of phi gradient psi is going to be, of course, you expand it out. It's a chain rule essentially, or yeah, okay. And so you get 5 or the derivative of the product essentially. So phi del square psi plus gradient phi gradient psi, right? So it's a gradient operator applied on the, so the divergence of the product gives you this, one of the term involves the Laplacian, the other term involves the, actually I should be careful here. I'm going to move this a little bit here. Both of these are vectors. And so it's going to be a dot product there, right? So this, you expect this divergence of a vector, you expect it to be a scalar. And so that needs to be a scalar, and that needs to be a scalar. So make sure you always check your expressions to see that they have the right kind of character, vector character or the scalar character. And so then the right-hand side is going to become, now the volume integral is going to become the volume integral of two quantities, phi del squared psi plus grad phi grad psi. And I'm not going to now you understand the character, so we're not going to write all the parts. And then the right-hand side is going to be the surface integral of ds dotted with phi gradient psi. Okay, everybody with me? I'm going to put a box around it because this thing has a special name. And it is called Green's first identity. And the scalar fields phi and psi are completely general. So if you take any two scalar fields and you evaluate this kind of quantity, it will be always true, right? So that's the first identity. Now, there is no reason why there should be a specific order between phi and psi. If you interchange them, you're not going to get anything different, but some of the terms might change slightly. You can see this term looks asymmetric in the interchange between psi and phi. The rest of the terms are not, and this term maybe, right? Because that involves the gradient of one of the functions, not the one of the fields, not the other one. So let's see what happens if we take the order to be different. Right? So now we have psi graph phi, and let's use now Green's first identity in this context with the role of phi and psi interchange. And so you're going to have now psi Laplacian applied to phi plus gradient of psi dotted with gradient of phi. And that, the second term is not going to change. It's going to be exactly the same as in the previous case. And the last term, of course, is going to be slightly different as well. Everybody with me? That's essentially just the Green's first identity, except psi and phi are interchanged. Okay, I'm going to call this expression A, call this expression B, and we are going to subtract the two. When we subtract the two, you can see the symmetric terms, they will go away, and only the asymmetric terms will survive. And so on the left-hand side, for the volume integral, it's just the difference between the Laplacian terms that will survive, right? Because for the dot product, even the dot product of the gradients, the order does not matter. And so this is what you will have on the left-hand side. On the right-hand side, everything survives because it is asymmetric to begin with. So you will have phi gradient psi minus psi gradient phi. Okay, everybody with me so far? This is also very important because it has a special name. And it's called Green's second identity. Okay, so that's how the second identity looks like. We will be using them later on. So, I will point out when the time is right on how to use them and what to make of them. But these apply to any set of two scalar fields, right? So these are very, very general, and that's the power of these things. Okay, very good. So I think that should do that for now. You could do something similar for a slightly different expression for f. So we're just going to quickly write those down as well. Let's take f, and these one I won't rigorously prove. You can go through them. So now we took two vector fields, so P and Q are two arbitrary vector field. And so there we have, we're going to get the divergence of the cross product. You know how to evaluate that. It's something you can use Levi-Civita symbols and convince yourself that this is how it's going to turn out to be. I made a mistake here. It should be a dot product crossed with B. Okay, so B dotted with curl of A minus A dotted with curl of B. Okay, and because it's a divergence, everything is a scalar, so everything should be fine. Now we get, let's say, an expression C here, which is going to be the volume integral of F, which is del cross P dotted with del cross Q. So here what we have done is that's our vector B, let's say, and that's our vector A. And then you can use the expansion that we just found in writing down the left-hand side of the expression. The right-hand side of the expression is just the F itself, the flux of F, which is P curl of Q, P crossed with curl of Q. Okay, everybody with me? That's again another form of Green's first identity for two vector fields. So this is still a first identity, but it now involves two arbitrary vector fields. And we can do something similar if we change the order of the two. Let's change the order of the two vector fields. And we are going to get gradient of, the curl of Q dotted with curl of P minus Q dotted with gradient curl, another curl of P now. Right, so where is that coming from? A with the curl of P. So A dotted with curl of B. So the other function. Okay, I'm writing this quickly, but it's straightforward. There is nothing new here. And Q crossed with curl of P. Right, so just interchanging the order of the two. Let's call this D. So now we have the two functions. So we are going to now subtract the two. We do C minus D,
Kapale,
and that's going to give us, yes.
so third term is minus or the one is?
Oh, no, sorry, this should be equal to, yeah. Okay, now which terms are going to survive? Let's see what happens here. This is completely symmetric, right? It's a dot product of two curls. So whether you do the first one and the second, it doesn't matter. So those terms are identical. After you subtract, they will go away. You can't say the same thing about the second one, right? So these terms are going to survive. This term will survive. And same thing over here. They're not symmetric in the interchange of Q and P. And so these are the terms that will be around after you have done this. So let's write this down. We are going to get, we're going to get inside the volume integral. It is going to be benefit. Okay, sorry, the negative sign, right? So we're going to get Q dotted with curl of P minus similar term for P and Q interchange. So P dotted with curl of Q. That's all that Q will have in the volume integral part. And on the surface integral part, you will have just the subtraction of the one vector crossed with the curl of the other one, minus Q crossed with curl of P. And that is called the Green's second identity for two vector fields. So both of these were the first identities. And you have two of those because you had two fields. And then Green's second identity in the case where you have two different vectors. Okay, so that's how that process sort of works. Any thoughts, questions at this time? So we will, use those later. Okay, now it's time to talk about the delta function, not the Kronecker delta that you're familiar with. I'm sure you have seen the delta function, and I had given you a reading assignment. So I'm hoping you have done that. So I'm just going to quickly review a couple of important properties of Dirac delta function, and then we will actually start using it for a variety of different things. So the interesting thing to note about the delta function is that it's not really strictly speaking a function. If you tell a mathematician, they're not going to like to call it a function, because function needs to be sort of well defined, needs to have continuous derivatives, that sort of thing. On all of those criteria, delta function doesn't really fit into those scheme of things, right? So this is something that you could see, it's named after a physicist, not a mathematician. It's the Dirac delta function. And it's essentially a filter function. Right? You think of delta function as a filter function. It filters out some specific values that you are looking for. So what we are going to use instead of delta x, let's say I'm going to change the argument to delta x minus x prime. And the delta function, because of the way it behaves, it is 0 when x is not equal to 0, and it's not defined to have any finite value at any other point or at x equal to 0. It is basically defined through an integral. So delta function is defined only through the integral. So that's the definition. Without that integral, the delta function has no meaning, right? You can't really ascribe a specific value to it. But you can think of delta function as a limiting case of variety of different functions, and the book gives you the list of them. Let's write down a couple of them. Limit m going to infinity of sine mx over pi x. It's going to give you a delta function, which will be 0 everywhere. But if you integrate from minus infinity to infinity, the integration will be 1. Okay, so the integration is finite. The value may not be. Right, and there are a couple of others, so we won't go into the details there. Okay, so what do we mean by filter function? That means if I do an integral now, negative infinity to infinity over certain parameter, let's say x, and I do an integral of f of x multiplied by delta of x minus x prime. Okay, so x prime is a specific value. Value of x, and you are integrating over the whole domain. Then what this does is it's a filter. What it does is it just picks out the value of the function at x equal to x prime. It picks out the value. So you could, if you want to think about how this would work, let's say I'm plotting the delta function to be something that has a sharp peak at x equal to 0. or let's say x equal to x prime, right? And then I may have some other function that is doing this, let's say f of x, and that's delta of x minus x prime. And then all that you do as a combination of this, this is essentially a convolution integral. When you integrate a product of two functions over a certain domain, that's just called convolution, because the behavior of one function affects the integral. And in this case, it just turns out delta function turns out to be a filter function because it pulls out the value of the other function at the point of interest, right? The interesting point, which is the x prime. Okay, everybody with me so far? Okay, so what are we going to do with this stuff? So let's actually take a look at, let me see if you have any questions at this point.
Kapale?
Yeah.
Could you please little scroll down because I missed that one.
Yeah, sure.
I'll take just a picture and then copy. Thank you.
Okay, very good. So let's take a look
Dr.
at,
Kapale?
yeah.
Actually, what's the basic difference between the Kronecker delta and Dirac delta?
Yeah, Dirac delta is a continuous function. X can take continuous values. The Kronecker delta has indices. Kronecker delta is a tensor. Dirac delta is a function. In sort of a loose definition of function. Does that make sense? So one
Yeah.
is continuous versus the other one has two discrete parameters. Because I and j, they're not, there is no x there for the Kronecker delta, right? Symbolically, delta ij and delta x, there's just no equivalency between them. They're very different quantities, even though we use the same symbol for them. So, we could have done something different there. Okay, so let's take a look at one identity of the delta function. The delta function identities are crucial. You may have seen them, but let's actually prove one of them so that you understand, how to play with the delta function. So let's take a look at maybe delta of ax is given to be 1 over amplitude of a delta of x when a is not equal to 0. Okay, so how do we prove this? Any thoughts? Okay, so let's work on proving this. The delta function identities, again, remember, delta function is defined through an integral. So without showing the integral equivalence, you can't really say the left-hand side is equal to the right-hand side. You have to integrate both of them with respect to some function and then show that the final answer that you get is essentially the same. So let's start with some function f of x, delta of ax dx. Okay. And the domain is the same, minus infinity to infinity. How would you simplify this? This is going to be, now you need to do a change of variable because it's the argument of the delta function and the integration variable. They are slightly different, right? And so I'm going to substitute, let's say y equal to ax. And so dy is going to be a dx. And inside, let's see. Dx is then going to be dy over a. Okay. And just to kind of keep things simple, let's split the integral into two parts. So minus infinity to 0 f of x delta ax dx plus 0 to positive infinity f of x delta ax dx. And so in this part, remove this here. And over here, the dx is, we just to kind of take care of the signs, we take y to be the amplitude. And so that's why you have this here. Strictly speaking, it should be like that, but that's perfectly fine. No integral dy, if you just make sure you are integrating in the direction of increasing dy, increasing y, then that takes care of it, right? So let's do the change of variables and let's see what we find, right? So f of x would become now f of y, right? So x is equal to y over amplitude of a for this part, and so on. So y over sine of a delta of y and dy over amplitude of a plus 0 to infinity. Since everything is positive here, you don't need to worry about that. But you can just write down modulus sine of a, that doesn't matter. Y dy over a, it works in both cases. It's positive anyway. And so eventually what you obtain is, you can see what has happened here, right? The integral will be, delta y would now behave as a filter function. You can take the a out, right? It's going to behave as a filter function, and it's going to pull out the value at y equal to 0, right? So that means it's just going to behave like delta x. Everybody with me? And that means I can say that delta of ax is nothing but 1 over absolute a delta of x, by looking at, again, comparing with this, f of x dx, f of x dx, delta of ax is now replaced by delta x with that. So that's how you kind of prove the identities of the delta function only through their integral properties. It does not work otherwise. Make sense? Everybody with me so far? Okay, there's another one that you can do using integration by parts, and I think let's go through that carefully, because integration by parts is another very, very important technique that's commonly used in E&M. Okay, so you want to evaluate something like this. It's an integral that involves a certain function f of x multiplied by the derivative of delta of x minus x prime with respect to x. Okay, so any thoughts on how we would go about doing this? So by itself, because the derivative of the delta function, that's not a very easy quantity to evaluate. So you want to remove that derivative from the delta function and move it to the other function. And the best way of doing that is through integration by parts. But let's see where the idea of integration by part comes in. And those of you who took math physics with me, I think we probably went over this earlier. But let's take a look at this. So if you want to take the derivative of a product, b of uv, it's u dv plus v du. This you know, that's very easy to remember. Now we integrate on both sides. So integration of d uv equals integral u dv plus integral v du, right? And this part, they are opposite of each other, so you're just going to get uv back equal to integral u dv plus integral v du, right? So that's something that's very easy to see. Now we are trying to find out this quantity, right? So we're going to just bring that on one side. It becomes uv minus integral v du. Everybody with me? And this is what we call integration by parts. And you could see the derivative of one of the functions, derivative of v, has been now moved to the other function, the u on the other side, and in between you get the product of the two. So let's take a look at that. Let's write this down. And this is evaluated, of course, at the boundary. If you have a definite integral, let's say a to b u dv, then you evaluate uv at the boundaries minus the integral has the same limit v du. Okay, so that's how that process works. Let's put a box around this also. Both of these are perfectly fine, depending on whether you have a definite integral or a indefinite integral. Okay, so let's apply this idea to this integral that involves a derivative of the delta function. So let me just copy this again. Okay, so let's take a look at that. Anybody wants to help me there? Okay, how would we do this now? Now that we know how the process of integration by part works. So uv term would be f of x times delta of x minus x prime evaluated at minus infinity and infinity. What do you think will happen there? What's the delta function at minus infinity and positive infinity? We assume that x prime is finite, right? So this is finite. So this is going to be equal to 0, right? Because in both the boundaries, it's 0, so we don't have to do anything. The other term would be now negative minus infinity to infinity. The limits stay the same. The derivative now is moved to the function. And so that's f prime of x, if you want to use the shorthand notation. And this is just going to be now negative df over dx evaluated at, remember, delta function is a filter function, so it's just going to pull out the value of the remaining part of the integrand at x equal to x prime, right? So using the filter function property. So if you have derivatives of delta function in your integrand for some reason, you have to move those derivatives to the other function, and then that's how you can do it. Or you can actually just directly use this identity that we derived, and you don't even have to worry about it. The moment you have derivatives of delta function, it is essentially equivalent to the derivative of the function evaluated at that special point, x prime, x equal to x prime. Okay, everybody with me? So that's another interesting property of that. There is an example that the book goes through, so I will let you do that. We're not going to go through it. Let's actually now combine the couple of different things that we have learned so far and start putting the delta function to use. Some formal use, if you will. Okay, everybody ready for that? Okay, so here's our task. Use divergence theorem to prove that Laplacian applied to 1 over r is equal to negative 4 pi delta of r. Okay, so that's the idea. And again, you could see you need these integral theorems because the delta function is not defined by itself. It is defined only through an integral. So you need to have the right kind of integral to be able to do that, right? And so let's start working through this problem one at a time, and then we will show that there is equivalence with the delta function. So what is this? 1 over r is sort of like the term that you encounter in the potential, either the gravitational potential or the electrostatic potential. It has this 1 over r dependence. And so, 1 over r is just simple functional simple function of position, which if you take the Laplacian off, it is going to look like that. That's what we want to prove. But what we are going to do now is use spherical coordinates. Okay, so give me just a second. I'm trying to adjust something here. So we want to use the spherical coordinates to evaluate this Laplacian. Anybody has any ideas on how one would go about doing it? Cool. Since it's only a function of r, you only need to include the partial derivative with respect to r terms from the expression of the Laplacian in the 3D spherical coordinates. And I gave you this front flap from the Griffith's book. That's what we are going to use. So again, you don't need to remember it. You can just read it off of there and then convince yourself that the r dependent term is going to look like this. So 1 over r squared, that's just the extra coefficient that comes in front. Then you have derivative with respect to r squared, derivative with respect to r of whatever the function is that you're trying to find the derivative of, right? So this is not crucial. This is the one that's crucial. And since we are, trying to find the Laplacian of 1 over r would go here, right? So the rest of the stuff just comes from the expression of the Laplacian in the 3D spherical coordinate, the r dependent part, right? There is also theta and other part we are not going to worry about this. And we are also going to now look at special cases when r is not equal to 0. Because when r is 0, things are a little different. So let r be not equal to 0, and then let's see what happens. I'm going to just bring it down to the next page here. So if r is not 0, then what happens? Then we know that this quantity here is not going to blow up. And if it's not going to blow up, we can then simply evaluate it. So we are away from the origin. It's easy to evaluate those derivatives. So del square of 1 over r is going to be 1 over r squared. Partial derivative with respect to r of, let's complete that derivative. So derivative with respect to r of 1 over r is negative 1 over r squared. So I just evaluated the inside derivative, and you can see this quantity now is constant.
It's a -1.
Right, -1. So what would be its derivative with respect to r? Any thoughts? Derivative of a constant is
0.
0. Okay. So when r is not equal to 0, the function that we are interested in, which is del square 1 over r, is 0. So that is satisfying the first property of the delta function. Okay, let me just go jump back to when we define the delta function here. The first property is that x is not equal to 0, the delta function is 0. So we have defined that part. We have to, of course, still to define the second one, right? So let's go ahead and work on that, and then we will be able to establish that equivalency between the two quantities. Everybody with me so far? You're okay with that correlation? So let's take a look at the behavior at r equal to 0. What's going to happen? So we are going to now use a divergence theorem for that. I'm going to take the volume integral of del square of 1 over r, which we can think of this as a divergence of the gradient of 1 over r. Everybody okay with that connection? So this is our vector function, a vector field, of which we take the divergence, and then we're going to use the divergence theorem to establish the equivalency of the volume integral with the surface integral of the flux of the function, which is gradient of 1 over r. Okay, everybody with me so far? Okay, and so this we have to do only for r equal to 0, around the point r equal to 0. And so this integral ds of gradient of 1 over r is going to be negative r hat over r squared. Everybody okay with that? Again, you could take the 3D expression or 3D spherical expression for the gradient, and the r component of that would be just negative 1 over r squared, right? It's just derivative. It's basically r hat derivative with respect to r of 1 over r, right? Which is going to be negative 1 over r squared. It's going to be this. Everybody okay with that? I'm hoping I'm not assuming too much, right? That is something you can quickly evaluate, and just look at the, again, the front flap of Griffiths, and you will know how that works. If you wanted to evaluate it rigorously, convert it into Cartesian coordinates, and you would still be able to do it, but it's going to get tricky because of the different transformations that you have to do. So make sure you're comfortable with that level of math. I have provided you the resources to be able to do that. First resource is the front flap, which has the expressions, but the appendix in Griffiths is actually the main resource, where it goes through the mathematical arguments as to how we come about. Come to that. Okay, everybody with me so far? So now our goal is to evaluate these surface integral and of this quantity r hat over r squared. And since we have the surface element on a sphere of radius r is going to be r squared sine theta, because you're at a specific value of r is not going to change. You're going to have d theta and d phi, and so the volume element or the surface element should have the dimension of length squared, which is where this r square comes from, and then you have the sine theta, d theta, d phi in the direction r hat, because the surface element also has a normal vector, and the normal vector in this case is going to be radially away from the volume of interest, right? And so it's always pointing away from the volume, and so the surface integral then becomes integral, with the negative sign, of course, coming from the derivative, so that is still there. Since you have two variables, you will have the ds integral now has to be transformed into two different integrals, one for the phi, which goes over 0 to 2 pi, and the another one over pi, which goes from 0 to pi, d theta, sine theta, and r square cancel. So you just have basically negative, right? So r squared, this r squared would cancel with 1 over r squared coming from the divergence. And so this is all that you are left with, which is going to be negative. Oh, sorry, I shouldn't be mixing these two. Let me move this. That's not what it's equivalent to. I'm going to put a box around it. Okay, everybody with me? And so you get negative 4 pi times 1, right? So negative 2 pi from the d phi, a factor of 2 from the pi integral, from the theta integral, and I don't even need this, just negative 4 pi. Okay, and negative 4 pi times times 1, because it's a filter function, right? And so if you think about this, the volume integral of d cube r del square of 1 over r, when r is not equal to 0, it is negative 4 pi times 1. I mean, it's not quite 1. If it is 0 when r is not equal to 0, so it follows the delta function property correctly. But the integral over the all volume of space is not 1. It has this extra negative 4 pi that it comes with, right? And so we could think of this basically now as del squared 1 over r would now become negative 4 pi delta of r. Okay, because r is equal to 0, you know, it just everybody with me? Does that make sense? So it's just a correspondence between those two properties of the delta function. We showed that del squared 1 over r also follows both of those properties. It's 0 when r is not equal to 0, and it is negative 4 pi integral over the whole volume of space. And so that's negative 4 pi times what you would expect from a delta function, which is 1. Everybody with me so far? Okay, why would we even bother doing this? Why do we have to express the Laplacian of 1 over r in terms of the delta function? That will become clear later. There is tremendous amount of advantage in doing that, because the integrals that involve delta functions, they are essentially trivial. And so expressing things like that as delta functions is actually quite powerful. Helps most of the tasks of finding electric and magnetic fields, which are almost always expressed in terms of integrals. You saw the Coulomb law expression earlier, and it just makes calculation a whole lot easier. So these are, again, E&M is all about knowing your calculational tools and practicing them and getting sort of acquainted with them. Okay, everybody with me so far?
Excuse me, doctor, I have a question, please.
Yeah, go ahead.
I was wondering if it's possible to, I mean, if manipulating with the last identity that you proved, which is the Laplacian of 1 over r equals minus 4 pi delta r.
Mhm.
If we can manipulate with it, is it possible to take the delta r to the left-hand side and make it 1 over delta r? Is that possible or not?
1 over delta r. Yeah, 1 over delta r is not very useful, right? What you can do maybe, right? So if you just want to manipulate this, the best place for that is, so let's actually, since you know a little bit of E&M, I can actually point out the usefulness of this, right? So let's take a look at this. What is del squared of 1 over r? It is divergence of the gradient of 1 over r, right? What is this quantity? If you look at the scalar field, v as a function of r, it is normally written as some charge density rho of r d cube r over r and it's actually also has, let's actually be using the MK system. So you will have, I'm going to move this thing here. So I'm kind of in some sense jumping ahead, but assuming you have certain background. So this is okay, right? That's what it's going to look like, right? So V of R, and that actually happens to be a scalar function of R. So everything is scalar there. Gradient of 1 over R is going to help you figure out the gradient of V. Sorry, gradient of V is not a vector field, gradient of V, which is proportional to, so the negative gradient of V gives you the electric field. And so when you want to calculate the divergence of the electric field, that basically gives you something that is going to involve Laplacian of 1 over R. Okay, and then the divergence of the electric field is through this relation is related with this rho of R. And so there's going to be rho of R times the delta function. And it just makes the integrals, the integrals of this kind very easy to evaluate because the integrand now is expressed in terms of the delta function. And so you can simplify things quite a bit. That's where actually the divergence theorem comes in. Another implication of that, because of this 4 pi, which is coming because of it may seem like it's coming because of the full and nice spherical symmetry, but that's not the case. If you have, let's say, some charge density here, I'm going to just color it like that. That's the charge density, rho of R. And if you want to enclose this with some arbitrary volume, it doesn't matter what shape it has. I'm going to just use a different color for the volume. So this is an arbitrary volume V. Actually, I should use a different symbol for that. Okay, volume V. And this V and that V is different. That's the electric potential, right? So this is the scalar potential. Sorry for the bad choice of letters, but that's the idea. So the volume enclosed does not have to be spherically symmetric. It's because of this delta function character, how the delta function behaves, that 4 pi will always cancel, and the divergence integral of the divergence of E is always going to give you the enclosed sum over all of the enclosed charges within that volume, no matter what is the shape. It doesn't have to be completely symmetric. And this actually comes from this interesting property here that we found. It relates with the delta function. So it just picks out those charges individually. Remember, delta of R is essentially you will have delta squared of 1 over R minus R prime, which will be negative 4 pi delta of R minus R prime. And R prime is the location of the charges. Right, so it picks out the locations of all the charges and you sum over all the charges. If you have a continuous charge distribution, that's just the total amount of charge, So for continuous, it's just rho of R, d cube R. That comes, rho of R prime, d cube R prime. This is coming because of that delta function. So Gauss's theorem, actually, strictly speaking, comes from this property. Remember, this is completely geometric. Right? There is no knowledge of E and M that we required to be able to figure this out. But when you apply it in the case of the electrostatic situation, then this is what gives you the Gauss's law, right? So this leads to the Gauss's law. And if you look at, there is, if you have looked through Griffith's discussion of Gauss's law, he tells you that you normally take these volumes or the surfaces that are covering the charge distribution to be symmetric, to follow the symmetry of the charge distribution. That is for convenience. It does not matter what the shape of those is. It is always going to be the charge that is enclosed by that volume. And that's because of this geometric property of a three-dimensional space. The volume integral of the theta and phi is always 4 pi. Does not matter so much on the r part there. Okay, everybody with me? Does that kind of make sense? So what the previous discussion so far was related to the geometric property, which is the Laplacian of 1 over r is negative 4 pi delta r. And we can connect it with ENM, and it leads to the Gauss's law, if you will. Does that kind of help, Khalid?
Yes, doctor. Thank you very much.
Okay, yeah. And you don't want to put delta function in the denominator. That's not very helpful, right? It's good by itself. So because you can integrate it, a denominator is going to be tricky. Okay, so I think what's the time now? Yeah, so we are up time-wise. So I'm going to stop here.